Now we will see the concept of junction breakdown, that how the junction is break and what are the mechanism that is added to that. So generally when a reverse bias voltage is applied, we came to know that when a reverse bias voltage will apply to this PN junction, so when the reverse bias voltage is applied, then there is a current which is a value. Suppose this is for my reverse bias, this is for reverse bias. What is this? In the third quadrant, that is my voltage is negative and my current is that is also negative, that is in third quadrant. So when this voltage is negative, that is in reverse bias case, up to some value the current remain very minimum, that is in nanoampere or microampere range, this is that is equal to minus is. But at a certain point of voltage there is a sudden rise of current. This region is called breakdown region. This region is called breakdown region. It is a voltage that is called RB. It is occurring at reverse bias case and that is breaking down. So that is the voltage RB, that is a reverse bias voltage at which the junction it is become breakdown. Breakdown means a high amount of current. You can see here the current value is very high. Since this is the current axis, the magnitude of current is very high. So this region is called breakdown region. So there are two mechanisms for this breakdown region. What? One is Zener effect and second one is avalanche effect. Okay, so this breakdown occurred for these two mechanisms. One is Zener effect, one is avalanche effect. We will see that one by one, and I will make a difference between these two so that you can get more clarity. First, remember this avalanche effect is done. Avalanche case, my number of doping, number of Na and Nd are less. If my doping I have done less doping means my P side is less doped and N side is less doped. If my doping is less means what will be my width? Width will be high. Remember the formula. What is the formula for width? W equal to 2 epsilon S upon Q V naught minus V reverse bias voltage 1 upon Na plus 1 upon Nd. From this formula you see, if I decrease my Na and Nd, so what will become my width? So it will become increase. Now this is my width. Okay. This is my width. Here I am applying reverse bias voltage. So this is my N side, this is my P side, this is my junction. So in N side, holes are the minority carrier. Here electrons are the minority carrier. As this reverse bias voltage increase, this region, this depletion region having a high electric field already there. So because of this voltage also the electric field increased. So this hole started swept to this direction and electron started swept to this direction. So what happened? Inside this there are, in P side it is negatively bound charge, in N side it is positively bound charge that is present over there. So when this electron or electrons are coming this side, while holes are coming this side. Holes coming this side, electrons to that side. When electrons are going that side, what happened? They are colliding with the bound charges present over here. It is one electron which is moving through this depletion layer and it is colliding with the bound charges. It is the bound charges means there are electrons present over there. There are electrons present at the outermost shell. These are the bound charges that are showing. So when this electron is colliding this one, it is reflecting me one electron that was already there, and when it collides it again give me another free electron. When another electron it is colliding with this atom, this bound atom, it is giving me 2 electron. So when these 2 electron again moving through this, they are colliding with another atom which are having valence electrons. So they are having again giving me maximum number of electron. This process, why they are getting some kinetic energy? When they are getting some kinetic energy, they are colliding with someone. When they are colliding with someone, we know that kinetic energy K equal to half mv square, that is mass of that electron and with some v. So with this kinetic energy they are moving with some velocity. With the kinetic energy they are producing more number of free electron. So as they are producing more number of free electron, they are going to give me a current whose value is very high. Because I am getting more number of free electron, this free electron will be responsible for this current conduction. So start what happened, how it happened, when this voltage is increased, this minority charge carrier, because of this electric field, they start influence to this electron to n side and holes to p side. So when this electron start moving to n side, they are colliding with the bound atom that are present over there, with the bound atom. With that much energy they are colliding and they are creating more number of electron. Again while they are moving through this depletion region, they are again creating more number of electron. So like this way they are creating more number of electron at the end. Remember what do you mean by avalanche? Suppose this is a mountain which is full of ice. This is a ice mountain. So when a big ice stone when falling down, what it is doing? It is colliding with some of the ice that is again stone that is present over there. These two again colliding, and at the last what we are getting? We are getting a high maximum number of ice stone, or that is in flooded way. So this is the process called avalanche. One is coming colliding with one, creating again two, again these two colliding with another one, again creating 2 to 4. So like this way you can see the electron, they are coming, they are colliding and creating maximum number of electron. So in this process, this is called impact ionization. This is the impact ionization that is done in avalanche case. What happens? This current is increased so high. So what is the voltage at which this avalanche effect occur? As I told, this is my graph. So this is the voltage, this is the current. So this voltage, if I let's stepping RB, reverse bias breakdown voltage. So when my VRB equal to VRB value greater than 7 volt, when this voltage greater than 7 volt, then that avalanche effect will occur, and at this case the current will be very high. So generally this case not occur at diode, because if this case will occur at diode, then the diode will burn out because of this high current, and high current leads to high power. So this high power dissipation means this diode will burn out. So along with the diode, what we do? We connect a current source, a series resistance. That series resistance will obstruct the current, high current. So if it will not connected, then the diode will be not able to work properly, it will burn out. So if this voltage, we are moving this way, this is the mod, means the negative side voltage. If this voltage will greater than 7 volt, then this value will be high, and it will be case for avalanche effect. And avalanche effect, the impact ionization process is done. Okay, now come to the Zener effect. So Zener effect occur at Zener diode. In Zener diode this process occur. For Zener diode, when my voltage, that's VRB, is less than 5 volt, it means it is the case when it is over here. It is for Zener diode, it is for V avalanche, I can say. It is for V avalanche, it is for V Zener. You can see this value is 5. When this voltage is less than 5 volt, then Zener case occurs. And for Zener effect, my Na and my Nd should be very high. Means the both P and N side should be highly doped. Highly doped means I can write in place of P, I have to write P plus, means it is highly doped. N plus, it is highly doped. If my doping will be high, what will become my width? Width will become less. From the formula same over here, if my doping will be high, this value give me less value. So W will be less. It means the width of the depletion region is very less as compared to this case. So as the width is very less, I am applying a reverse voltage. Here electric field was there in this direction, and again because of this voltage, again voltage is coming in this way. So again the electric field that is across the depletion, that is also increased. So this combined electric field increased with a high value. Okay. So here similarly for in the previous case, here also some minority charge carrier and over electron in the P plus side and this N plus side. As this is highly doped, it means at this less width also makes more number of ions are there, that the bound charges are there, because it is highly doped. Here it is lessly doped. So at this much width, less number of bound charges are there. But as this is highly doped all over here, these are the bound charges. You see, as compared to previous one, more bound charges are there because of the heavily doped. So heavily doped, this means this region having high electric field. So this electric field will, what will do? This electric field will force this electron to move to this side and this holes to this side. So that will conduct a current. But as the electric field is very high, it can knock out the bound electron that are present in the silicon atom. In this case, because of the kinetic energy, the electrons are increasing in this case. But in this case, as the electric field is so high, what is there? I am applying a strong electric field. Because some electric fields they are in the depletion, and because of the doping, high doping, that is also electric field. And I applied some voltage back. Because of that also strong electric field is there. So because of this strong electric field, the silicon atom that is present over here that are bound, that 4 valence electrons are there. When this electric field is flowing in this way, they are what? They are knocking out this electron, valence electron to this. So these valence electrons are constituting my current, a high current. So this process, since this width is very less, this occur for tunneling. Here the tunneling process occur. Here the impact ionization. One ion is striking with another, one electron striking with another atom, creating another more number of ion. So it is impact ionization. Here it is tunneling. Means this electron or these holes can easily tunnel through this small width. As the doping is very high, width is very less, so they can easily tunnel through this. And the impact of electric field will give rise to, can knock out the electron, that is the from these bound charges. So this constitutes the current. So that is nothing but here is the current. But when the voltage is less than 5 volt, this is the case, and when the voltage is greater than 7 volt, then this is the case. Then what is the case for when the voltage is 5 to 7? That case, in that case, it can be anything. When my voltage is 5 volt to 7 volt, it can be either avalanche or it can be either Zener. So that depend upon the external circuit that is connected to it. One more thing, this Zener effect, the temperature, now we will see the impact of temperature over here. So what happened? Here because of electric field they all are moving. So if I will increase my temperature, then what will happen? Because of this temperature, the minority charge carrier, that those are the present over in this inside here or inside here, they will also increase. So this increase again with adding with the electric field, there are also more number of hole pair, electron hole pair. So that means when if I increase the temperature, more number of electron hole pair are generated. That means the current is increasing. So for this case, I no need to supply any extra voltage. If this is the case for T1, when there is no added temperature, if I increase the temperature, then this is the second case for T2. My voltage will be less. This is V2, this is V1. Because why? If I increase the temperature, more number of electron hole pairs generated. It means the current is increasing. So automatically current is increasing. No need to add extra voltage. So this is the for T2. So here this is the negative temperature coefficient. It means if I increase the temperature, my voltage should be less. But in this case, what happens? If I increase the temperature, then I should increase my voltage also. Why? See, here the electron are coming and it has to strike with this atom. So if the temperature will increase, this atom start vibrating. So it was before over here, and the electrons is coming in this way, and it should strike this one. When it is vibrating, so the atom which is present over here, it might shift to this place, and this atom might shift to this place. So the electron which is coming to strike this electron is not able to strike this one properly. So for this reason, I have to increase my voltage so that electron will get that much energy, it should strike wherever that atom is present. So for this case, if I am increasing the temperature, my voltage should also be increased. So it is a positive temperature coefficient. It is the negative temperature coefficient because already because of temperature, minority charge carriers, that electron hole pairs that are creating. So this electron hole pair are giving me extra current. So no need to add extra voltage. That's why I can reduce my voltage. We will see the capacitive effect in an PN junction. That how charge is stored and what type of charge are stored. So there are basically two type of charge stored mechanism. One that is stored in the depletion layer of PN junction, that is called depletion capacitance or junction capacitance. That is the same, junction capacitance and depletion capacitance, that is one. And second, the charge stored mechanism, that is because of the minority carrier charge stored. That is either in P side, this P side or N side, there are some charge stored. That is called diffusion capacitance. So now we are going to learn this one. One is depletion capacitance and second one is diffusion capacitance. So the depletion capacitance, that is seen when there is a reverse bias voltage is applied, and the second one, that is the diffusion capacitance, that is for the forward bias condition. Now you tell me what is the formula that you wrote for that charge for when reverse bias is applied, that is A under root 2 epsilon s q v naught plus v reverse bias v naught plus vr whole into Na Nd upon Na plus Nd. Okay, this is the formula. So this can be right. This A and all this value can I write? This is one constant which is multiplied with V naught plus Vr, where my alpha is nothing but A times 2 epsilon s q V naught plus Na Nd upon Na plus Nd. This is my charge, which is nothing but some alpha constant times V naught plus Vr, which is a function of reverse bias. When reverse bias is applied, I am telling this is the depletion capacitance or junction capacitance. So at this value we can see, if I draw a graph between this reverse bias voltage and charge, it shows it is a non-linear characteristic. It shows it is a non-linear characteristic. It is not linear. So I want to find the capacitance. What is the formula for capacitance? Q equal to Cv. C is nothing but Q upon V, or I can write dQ upon dV. So here for this is the junction capacitance. I am writing Qj. So here it is Qj. In place of what is the second condition that is applied? Vr. Here it is Vr. So for finding the capacitance, I have to see that change in junction charge upon this voltage. But for Q, this graph is non-linear. So how I can find this value? For that, I have to take a point over here. This point is Q point, or it will call it as a bias point. Bias point. So the slope of this curve, this is the non-linear curve, Q equal to alpha times V naught plus, this is a non-linear curve. The slope of this curve, what will give me the slope of this curve? Will give me the value of Cj, that is the junction capacitance Cj. So I have to find my Cj, which is nothing but d of Qj upon d of Vr at this at Q point or my bias point. Okay, so it is nothing but d by dVr. What is my Qj? Which is nothing but alpha times under root V naught plus Vr. It is nothing but alpha is a constant taken out. What is d by dx of root x? Is nothing but 1 by 2 root x. So this is a constant. This is in terms of Vr means it is x is there. So it is nothing but x plus a, which is nothing but under root x plus a. So I can write alpha by 2 times under root V naught plus Vr. This is my Cj. Okay. Now this is when applied reverse bias. When there is no bias, it means when my Vr value is 0. At that state, what will my Cj? Cj will become Cj naught. Means at 0 reverse bias or equilibrium case. That is Cj at Vr equal to 0. So what will become my Cj naught, which is nothing but alpha times 2 under root V naught. So when Vr equal to 0, this is my Cj naught. So you can see my alpha, which is nothing but Cj naught times 2 into V naught. So in place of alpha, I can put this value. So my Cj will become Cj naught 2 under root V naught upon under root 2 V naught plus Vr. So these two cancel out. My Cj is nothing but Cj naught under root V naught upon under root V naught plus Vr. Or I can write Cj naught upon this under root V naught, and if I will bring it here, it will become under root 1 plus VR upon V naught. Okay, so my Cj is nothing but Cj upon 1 plus VR upon V naught power half. This is for this case. I can change this value. In place of half, if I write m, it will become Cj is nothing but Cj naught upon 1 plus VR upon V naught power m. M is called my grading coefficient. Which type of grading I am doing? M value can be 1, it can be 1 by 3. So based upon my grading, I can find my capacitance. Cj is nothing but Cj naught upon 1 plus VR upon V naught power m. If the grading coefficient is given half, so this will become under root of this. If it is 1 by 3, so m, in place of m you will put 1 by 3. So when our doping concentration at the this is the boundary, suppose this is my junction, this is my, when doping concentration change abruptly, it is called abrupt junction. When doping concentration change gradually, it is called graded junction. So based upon my concentration, I can find my capacitance value at the junction. Okay, there are two types, one is abrupt, one is graded. When it is changes, this concentration changes abruptly, it is abrupt junction. When it is changes gradually, it is called graded junction. This is the for junction capacitance. The second one, that is the diffusion capacitance. The second capacitance or the charge stored in this PN junction, that is the diffusion, because of the diffusion capacitance that occur when forward bias is applied. When forward bias is applied, some excess minority charge carrier, that is holes in P side, holes in N side and electrons in P side, they are stored. So these excess carrier gives rise to a capacitance. Before that we read that was the because of depletion. Inside the depletion region, the charge stored. Here because of the minority electron holes that are present. So we have seen before the excess electron or holes, that is the holes over here or electron over here. They are shown by this. This is the Pn naught, that is the holes that are already present at equilibrium. This is after injecting number of holes to this through this barrier or electron through this barrier. This is the graph we get before. So the capacitance means we have to find the C. C is nothing but dq upon dv. So for that we have to find the charge. So what is the charge in this region? Is nothing but area multiplied by this q, charge of each holes into shaded area under this PN. So what are the excess number of holes that are present in this region? That much times charge multiplied by area, that will give you a overall charge. So the shaded area, this is the region that we read, is nothing but concentration multiplied by this length. So this Pn of xn minus Pn naught into xp. We have seen this formula I have written on just to save your time. This is the Pn of xn is nothing but Pn naught e power v by dt. So what will become Pn xn minus Pn naught is nothing but Pn naught will take common from both. So e power v by vt minus 1 into Lp is over here. So what will my Qp? It will become, it is nothing but Aq Lp. Lp is over here. So this value I have written, in place of this value I have written Pn naught e power v by vt minus 1. Now remember, if this is the Pn, what will my Jp? Jp is nothing but q dp derivation of this one. So if I will derive this one, it will give me a Pn naught 1 by Lp e power v by vt minus 1. Okay. So here what I am doing, in place of Pn naught e power v by vt minus 1, in place of Pn naught e power v by vt minus 1, I am going to write in terms of Jp. So this value I am replacing Jp into Lp upon this value. So Jp multiplied by Lp divided by q dp. So 1 q was before there, so this q cancel out. It remains a Lp square upon dp into Jp. That is nothing but Jp square upon dp. A into Jp will give me a current, that is equal to Ip. So Jp square my tau by dp is nothing but my tau p. As I told before, what is tau? It is the excess minority charge carrier lifetime. That for how long these holes are penetrating through this N side and recombine, till that time it will recombine with the electrons. So that is the lifetime. So that is represented by LP square, that is the diffusion length for holes, divided by diffusivity of holes, dP. So LP square upon dP gives me the tau p, and this I into J multiplied with current A into J. Similarly, if I found this charge for Qn is nothing but AQ shaded area under this curve, under this Qn P of x curve. This is the second curve. So what will be this one is nothing but Np of x minus xp minus Np naught into Ln. So if I will again found from the same formula, same process, I will get my Qn, that is the charge stored for this region, excess charge stored in this region, is nothing but tau n and In. Okay. Now my total charge is nothing but Qn and Qp. So these two are added. So that is tau p Ip plus tau n In. In a diode, the current is nothing but Ip plus In. You remember this? For a diode, this is the current Ip plus In. And the tau p and tau n combinedly, can I write tau t, which is nothing but the mean transition time of this junction. In this junction, what is the mean transition time that I took in terms of tau p and tau n, that I wrote tau t. If I take tau t as common, so Ip plus In, which will give me a current Id, that is a diode current. Okay. Now I have to find my capacitance, which is nothing but derivative of this upon dB. This B is nothing but my VR. So tau IT, so tau T upon Vt into, that is the current I will get because of this forward bias current. So this diffusion capacitance will work for forward bias, but for reverse bias the diffusion capacitance is 0. But the depletion capacitance, that is for reverse bias case only. For forward bias the depletion capacitance will be 0. So this is my capacitance value at forward bias case. Now just remember one point, what I am going here, I am doping. If I will increase my Na bit higher than Nd, if I will increase the doping of Na will bit higher than Dp, then what will happen? Na means I am going to this P side more positive. If I am doing P side more positive, then the more current will flow. So my Ip will increase than In. So if Ip will increase, my I will become Ip and my Q will become Qp. My tau T, it will become tau P. Similarly, if my Nd, donor side I will doping more than Na, then what will happen? My In will be greater than Ip. Then my whole current is nothing but my In because of In, and my Q will become Qn, and the tau will become tau n. So these are some certain cases. Remember these cases are, if I will increase, how these values are going to change. So these are the two capacitance that is present in a PN junction diode. From next video we will see the ideal PN junction diode and what are the diode characteristics and some special diodes also.